So now we should be able to relate what we know about different frequencies and different wavelengths. So if Darcy, can you switch us over to a clicker question here? And we can also talk about the difference between what's happening when we have emission, and we're going to switch over to absorption. So we just talked about emission, so before we head into absorption, if you can answer this clicker question in terms of what do you think absorption means, having just discussed hydrogen emission here. So we have 4 choices in terms of initial and final energy levels, and also what it means in terms of the electron, whether it's gaining energy or whether it's going to be emitting energy. So why don't you take 10 seconds on that? We'll make it a quick one. All right, great. So already just from knowing the emission part, we can figure out what absorption probably means. Absorption is just the opposite of emission. So instead of starting at a high energy level and dropping down, when we absorb light, we start low and we absorb energy to bring ourselves up to an end final that's higher. And instead of having the electron giving off energy as a photon, instead now the electron is going to take in energy from light and move up to that higher level. So now we're going to be talking briefly about photon absorption here. So again, this is just stating the same thing. And it could take in a long wavelength light, which would give it just a little bit of energy, maybe just enough to head up 1 energy level or 2. Or we could take in a high energy photon, and that means that the electron is going to get to move up to an even higher energy level. And again, we can talk about the same relationship here. So it's a very similar equation to the Rydberg equation that we saw earlier, except now what you see is the n initial and the n final are swapped places. So instead now we have RH over Planck's constant times 1 over n initial squared minus n final squared. And what you want to keep in mind is that whatever you're dealing with, whether it's absorption or emission, the frequency of the light is always going to be a positive number. So you always want to make sure what's inside these brackets here turns out to be positive. So that's just a little bit of a check for yourself. And it should make sense because what you're doing is you're calculating the difference between energy levels. So you just need to flip around which you put first to end up with a positive number here. And that's a little bit of a check that you can do with yourself. So let's do a sample calculation now using this Rydberg formula, and we'll switch back to emission. And the reason that we'll do that is because it would be nice to actually prove what we just saw here and calculate the frequency of one of our lines and the wavelength of one of the lines we saw. So what we'll do is this problem here, which is let's calculate out what the wavelength of radiation would be emitted from a hydrogen atom if we start at the n equals 3 level, and we go down to the n equals 2 level. So what we need to do here is use the Rydberg formula. And actually, you'll be given the Rydberg formulas in both forms, both for absorption and emission on the exams. If you don't want to use that, you can also derive it as we did every time. It should intuitively make sense how we got there, but the exams are pretty short, so we don't want you doing that every time, so we'll save the 2 minutes and give you the equations directly, but it's still important to know how to use them. So we can get from these energy differences to frequency by frequency is equal to R sub h over Planck's constant times 1 over n final squared minus 1 over n initial squared. So let's actually just simplify this to the other version of the Rydberg constant, since we can use that here. So kind of that strange cursive R. And our n final is 2, so 1 over 2 squared, minus n initial, so 1 over 3 squared. So our frequency of light is going to be equal to R times 5 over 36. But when we were actually looking at our different wavelengths, what we associate mostly with color is the wavelength of the light and not the frequency of the light. So let's look at wavelength instead. We know that wavelength is equal to c over nu. We can plug in what we have for nu. So we have 36c divided by 5, and that cursivy looking Rydberg constant. And that gives us 36 times the speed of light, 2.998 times 10 to the 8 meters per second, all over 5 times 3.29 times 10 to the 15 per second. So what we end up getting when we do this calculation is the wavelength of light, which is equal to 6.57 times 10 to the negative 7 meters. Or if we convert that to nanometers, we have 657 nanometers. So does anyone remember what range of light 657 nanometers falls in? What color? Yeah, it's in the red range, so that's promising. We did, in fact, see red in our spectrum, and it turns out that that's exactly the wavelength that we see, is that we're at 657 nanometers. So it turns out that we can, in fact, use the energy levels to predict, and we could if we wanted to do them for all of the different wavelengths of light that we observed, and also all the different wavelengths of light that can be detected even if we can't observe them.